The objective of any classification algorithm is strictly mathematical. Take a p-dimensional input vector and map it to a discrete class label. Each classifier operates as a distinct mathematical philosophy, imposing its own geometric logic onto the exact same data space. This animated scatterplot illustrates how different algorithms slice through identical data points. The space is partitioned differently depending on the model. As the plot rotates, notice how boundaries misclassify specific outlier points because they defy the algorithm's rigid geometric shape. Because of the no free lunch theorem, there is no universally superior model. An algorithm's empirical efficacy is dictated by how perfectly its geometric assumptions align with the topological reality of the dataset. To test this theoretical premise, we can examine the empirical study by Shetha and colleagues, which evaluated 4 fundamental classifiers across diverse structured datasets. This data matrix plots the accuracy and F1 score results across 3 specific datasets: placement, heart disease, and wine quality. As the columns highlight, a distinct algorithm emerges as the winner for each unique data space. By dissecting the specific geometric and probabilistic rules governing these 4 models, we can identify the specific architectural features that drive performance within different data spaces. Model selection is a rigorous mathematical matching game between an algorithm's architecture and the data's dimensionality. We begin with k-nearest neighbors, or KNN. It is a non-parametric model that relies purely on geometric feature similarity to make its classifications. The algorithm utilizes Euclidean distance to compute the spatial boundary around a query point, either by a set radius or exactly k neighbors. The decision boundary dynamically shifts depending on this hyperparameter, expanding to absorb new points into the classification. This reliance on spatial distance introduces a severe architectural vulnerability, massive computational cost at scale. Because the model must calculate the distance to every single point, it incurs a computational cost of big O of n squared p. As a result, the model becomes highly vulnerable to noisy, irrelevant dimensions in the feature space. KNN's reliance on raw spatial proximity makes it powerful for pure geometric similarity, but computationally crippling in high-dimensional, noisy data spaces. Decision trees discard distance metrics entirely in favor of orthogonal, recursive partitioning of the feature space. At every node in the tree, the algorithm systematically searches for the exact feature and threshold pair that minimizes mathematical impurity, splitting data into subsets. This graph plots impurity on the y-axis against the proportion of a class on the x-axis, mapping the geometric curves of 2 criteria, Gini index and entropy. The algorithm uses calculations like Gini index to precisely measure dataset heterogeneity and enforce splits. Because these splits evaluate one feature strictly at a time, the unavoidable geometric consequence is that all decision boundaries are completely orthogonal, running perpendicular to the feature axes. This partitioning method creates extreme variance. If the tree's depth is left unconstrained, it will aggressively overfit the training data down to the individual node. While decision trees provide highly interpretable logic, their orthogonal rigidity makes them mathematically brittle to nuanced, nonlinear data variations. Support vector machines operate with a distinct mathematical objective, discovering the exact hyperplane that maximizes the margin between classes. Looking at this 2D plot, we see a rigid hyperplane separating 2 classes, flanked by dashed margin lines. This boundary is mathematically locked by the margin constraint. This boundary optimization is governed by hinge loss. Any point classified outside the margin returns 0 loss, meaning only support vectors dictate the entire boundary. The failure point of a linear SVM occurs when it confronts a non-linearly separable data topology. To bypass dimensional inseparability, the algorithm relies on a mathematical mapping workaround known as the kernel trick. Using a radial basis kernel, the model takes a flat 2D plane of intertwined data points and smooths them into a higher dimensional 3D topology. This allows a flat plane to cleanly slice horizontally between the clusters. SVMs are formidable because they mathematically transform inseparable topological problems into solvable linear geometry, though at the strict cost of high computational complexity. We now shift the analytical lens away from geometric spatial boundaries and toward probabilistic generative models. This formula calculates the posterior probability of a class based entirely on prior class distributions. it explodes into the product of individual probabilities, representing the strict axiom that all features are conditionally independent given the class label. This probability assumption enforces a strict geometric consequence on the data space. Here, normal distribution ellipses representing covariance matrices are rigidly constrained into perfect circles, eliminating any modeled correlation between features. Because the model ignores covariance entirely, this aggressive simplification drastically reduces the required training data volume and computation time compared to SVMs or KNN. This naive mathematical assumption completely sacrifices complex interaction modeling, yet it produces a highly resilient, noise-resistant classifier that frequently defies professional expectations. Returning to the empirical reality of the Shetha trial, we can evaluate how these algorithmic architectures performed against real data. The trial demonstrated that KNN routinely underperformed on F1 score, severely hampered by its inability to filter dataset noise. Decision trees consistently struggled with generalization across these specific datasets, explicitly due to their orthogonal rigidity. This split-screen visualization details the overall metric champions across the placement, heart disease, and wine quality datasets. On the left, bar charts plot the F1 and accuracy scores. On the right, annotations map the dataset topologies, contrasting continuous numeric inputs with discrete biological markers. The results isolate a distinct performance split. Naive Bayes dominates recall metrics, while SVM and naive Bayes aggressively trade blows for the absolute top F1 score, depending entirely on the specific dataset. These empirical results prove a critical professional reality. Complex architectural models do not universally outperform simpler probabilistic models on structured data. To understand exactly why SVM and naive Bayes traded empirical victories, we look to the data topographies themselves. SVM excels precisely when the data topology requires complex, high-dimensional boundaries manageable only via kernels. Naive Bayes dominates when feature independence holds mathematically true, or when continuous and discrete data mixes smoothly under its probability distributions. The chosen loss function, whether hinge loss or the impurity score or logarithmic scoring, is the ultimate arbiter of learning, dictating exactly how a model handles outliers and nonlinearities. Engineering a machine learning solution is never about finding the objectively best algorithm. It is an exercise in rigorously pairing the geometric and probabilistic assumptions of a classifier with the dimensional reality of the data space.